episode 239. Welcome to Data Skeptic, a podcast about data science and fake news from an algorithmic perspective. Here's your host, Kyle Polich.
So let's get back into Bayesianism. Why and when do we use Bayes' theorem? We have to start with conditional probabilities. So the likelihood of x given y. Are you with me so far?
Probability and x given y.
Let's put this in the context of our parrot Yoshi. So Yoshi eats many things. Can you tell me a little bit about the variety that's in her diet?
Well, we've now weaned her to eat mushy pellets and hard pellets, and then sometimes we give her treats like fruits and veggies.
And even if we don't give her certain things, she'll eat a broader class than we offer her, right?
Well, yes, she would prefer to eat something different every day, I think.
Okay, so that's interesting. So she has some sort of sequential preferences we don't totally understand. Now, are there certain things you could give her that she will always eat them, as long as she's not full?
I don't know about always, because if you give it to her too many days in a row, then she'll throw it out of her food bowl.
Okay, so good point. Like what about garbanzo beans?
She'll eat it for the most part, although if I give her too many, she doesn't care for them.
Can you share with the listeners a few details about how she actually eats garbanzo beans?
Yoshi is a parrot, so she likes to use her beak, and one of her main joys of life is peeling everything she touches. So if there's a blueberry or a garbanzo bean or anything, she likes to peel it and
Yeah, she
take
takes
out
the
a
skin
skin.
off.
She doesn't eat the skin. It's very important to her that she not eat the skin.
So let's say we had a new thing we were going to give her we'd never given her before. Actually, can you think of any fruits that we have not given her?
Have not given her a dragon fruit.
A dragon fruit. Why don't you remind some of the listeners what the heck that is?
Well, I don't really know how to describe it. It's a fruit and it can come in colors of pink. I've seen it pink and white, but the most common one I've seen photographed is that it's white with little black seeds in it.
So I think it's very popular in Southeast Asia, right?
I don't know. I haven't looked up a heat map. That's a good point.
fair
But I
enough.
assume it grows in the tropics.
What do you think? Would she eat that or not if we gave it to her?
I think she would.
So tell me a little bit about how you arrived at that conclusion, and then we'll talk about the Bayesian way you would think about it.
Well, everything we eat, we ask ourselves, what would Yoshi do? So in this case, Yoshi would probably find the texture enjoyable. It is not fully starchy. It's mushy and filled with liquids, and then there's tiny seeds in it. So she might get a kick out of that.
All right, so you're on the verge of defining it in a sort of a Bayesian way. You just listed off a bunch of features of foods she likes, and that's how we're going to kind of transfer our knowledge from what we know about other foods into this food, by its similarity, right?
Food similarity. Well, I think there are characteristics or traits that Yoshi seems to like.
And then we ought to include some time clauses as well, as you mentioned, like what she's going to eat today depends on what she ate yesterday.
Yeah, too much food of the same thing. She gets bored.
So we want to know the probability of some action, that the probability she'll eat the dragon fruit, given her history of eating, what we know about what she's eaten before. That's what we would like to know, and we're going to call that the posterior probability. Actually, does the word posterior come up? Do you find that to be in the vernacular, or should I define it?
Posterior. Does it mean outside?
No. Also, I often ask this of non-statistical people. Some people think it means your bottom.
So what does it mean?
Well, so what I mean by it in the Bayesian sense, it's what our statistical distribution should look like after we do a calculation. So you have the information you start with. We're going to call that the prior. This is just the wording of how Bayesians do things, so you'll have to get used to it. The prior kind of means what you know now, or the moment before you got new information. So our prior is, will she eat the dragon fruit? I don't know, maybe 90% likely. And we're going to base that on some of those similarity metrics we talked about earlier. Now, this part I'm going to skip over a little bit, because actually defining what the prior is one of the hardest parts about doing a Bayesian thing very well. Sometimes you're lucky and you have like a system or a dynamical system or something like that, and the prior from simulation or something like that. But in our context, will the parrot eat this fruit? We just have to go with the data we have available. So one methodology would be to come up with this model based on the features like you were kind of spelling out. So we have some prior probability. What would you assign?
What, for the dragon fruit? Yeah.
That's our prior. What we'd like to know is the posterior belief. So let's say we go feed it to her. Perhaps she'll try it and she won't like it, right? And she'll never try it again. We don't know. So we want to compute the likelihood now. And prior times the likelihood gives us the posterior. It's the process of how we compute our beliefs after we've integrated the new information.
How did you get your prior into a number?
Well, the prior is really a statistical distribution. So in this case, it's a binary variable. Will she eat it, yes or no? And we just assign 90% probability based on kind of our domain knowledge about the bird. Let's make the problem a little bit more difficult now so it's not binary. Let's say we offer her 10 different types of food. One of them is the dragon fruit, one is her pellets, one is a Brussels sprout, the list goes on and on. We want to have some distribution over which one will she eat first. Now, you wouldn't know for sure. What happens usually when you give her a variety of different foods in her bowl?
Well, me and you bet on what we think she'll eat first. Today, we had a variety of things in her bowl, and we bet that she was going to eat the squash, and she did.
Now, how did we get so good at guessing?
Well, squash is a good texture. What else was in there? Did I have orange peels? Yeah, I did. I had an orange peel and an orange, which she gets pretty regularly, so I don't think she'd be as excited about that. And I put some egg parts, and I don't think she'd be as excited about an egg as she would about a squash.
All right, so your prior probability is then distributed across all those foods. So maybe 90% squash, 5% goes to the egg, and the remaining 5% to whatever else is in there, pellets or something like that. In this case, we're saying intuition about what that distribution looks like. In some settings, there's a particular way you derive it, whether it be assigning equal likelihood, uniform belief over all of them, or sometimes there's some statistical motivation, like the more complicated a hypothesis is, the less likely a priori you assume it will be true.
So you're just saying I'm building my own model in my head?
You are if you're going to be a Bayesian machine, but if we're going to do this in a computer, let's take the example for the moment. We'll come back to Yoshi, but the example of GPS. Now, as you probably know, your GPS actually is very horribly inaccurate, right?
GPS, you mean Google Maps, or you mean like an independent GPS?
The GPS chip in your phone that's talking to satellites, or listening to them anyway.
How do you measure accuracy?
Well, the experience I think a lot of people will relate to is you open up a mapping application, Google Maps or otherwise, and it's going to put your dot on the map. And sometimes, especially if you've just rebooted or something, the dot will be close but not at your location, and then it'll bounce around and finally kind of end up where you are, right?
Okay, so that's a delay. Does that mean inaccurate?
Well, they arrive at that conclusion in a Bayesian way, most likely. So GPS, your phone is listening to a satellite. That's a complicated thing, and we want to know exactly where we are within like a meter. That's a very high accuracy problem, and those are satellites flying over us in space, and they have to do orbital mechanics, and they have to account for relativity and all this crazy stuff. It's hard to get accurate. So they're not actually showing you the true GPS reading every time, because the true GPS reading is very noisy. It's bouncing around. But the noise we assume is Gaussian distributed. So the average is going to do a good job summarizing your real location. So they take maybe 10 measurements in a row, or maybe the most recent 10 or recent 50. I don't know how exactly they do it, but they have some mechanism to kind of localize that by averaging.
Sure, so they're taking an average, and you're sounds like you're saying you think it's inaccurate.
No, not necessarily. That's a fine way to do it. Basically, you also have to worry about battery power and computational power. So I can't be sure they do it in a Bayesian way. Maybe they do it the way I just described, like average of the most recent 10. But you could also do it in a more Bayesian way, where you have your prior, where we think the person is. And if you just turn on your phone and you get one measurement, your best guess is that they're at that point. But then you have a high variance because you know that the GPS is inaccurate. So that's why sometimes there'll be like the big blue radius circle and it'll shrink. So that circle is really somewhat representative of a statistical distribution over where you are. And then as you get in new information, new observations from the satellite, you would say, what is the likelihood my position is here given these couple of observations? And so you flip that around with Bayes' theorem. The posterior equals the prior times the likelihood, and then you normalize. So set the normalization aside for a moment. Let's just work on the basic arithmetic. Posterior, what your belief is afterwards, is equal to your prior times the likelihood. So the prior starts out, in this case, we have a nice statistical model. We know that's sort of a Gaussian model of location. But in our case with Yoshi, where we're like, oh, which food will she eat? Then we have to have like a categorical distribution over those multinomial values of all the food that are in the dish. And ideally, our idea is informed by everything we knew before. Hopefully, our beliefs are what's called a sufficient statistic. So they summarize all the information we've ever learned about Yoshi. We don't have to rethink, the however many years we've been feeding her. We just think about what we have learned about her preferences. So that's our starting point. Thanks to the Great Courses Plus for sponsoring today's episode. Today I want to highlight one of their lecture series, Mathematical Decision Making, Predictive Models and Optimization. This 24-lecture series is presented by Professor Scott P. Stevens of James Madison University, and it is highly relevant to today's show topic. If you'd like to better understand how mathematics is used to model things, be it election responses under the influence of fake news, or literally anything else that happens in nature, you'll need to know some of the basic mathematical mechanics of systems. And that's exactly what you're going to get in the Mathematical Decision-Making course. You'll start out learning about operations research, and every data scientist should know about operations research. There's a heavy overlap with what data science is. Move on to regression and time series, clustering, linear problems, all the tools you need to successfully model how the world works mathematically. With the Great Courses Plus, you'll get unlimited access to stream their entire library. That's right, it's not just mathematical decision making, it's every single lecture they've got, thousands of them. And right now, they're offering Data Skeptic listeners unlimited access to their entire library for free. Take it with you on the go with the Great Courses Plus app. Watch or listen anytime, anywhere. These lectures average 31 minutes. I bet you can squeeze one in every day of your commute. Sign up now at thegreatcoursesplus.com/data. That's thegreatcoursesplus.com/data. Now, of course, her preferences could change day to day, like you said. So then we need to update our beliefs. We need to know the likelihood. First of all, there's a couple of, we could call them hypotheses. Like maybe we could think, oh, she tries new foods often, or she tries foods she hasn't seen in a while, or she loves garbanzo beans. These are all kind of theories of her behavior. And we want to know which one is the accurate one. We want to know the likelihood that we would see her take a certain action, like eating the squash, given that she loves squash, or given that squash has features we know she appreciates in food. So we also have to know that statistical description of our process. And this is where you sometimes get into trouble. Sometimes the ideal way to do this stuff takes really, really complicated mathematics. Not so much complicated in terms of, you have to have an advanced degree, but in terms of it takes a large amount of computational power to compute it. So sometimes you get into approximations here and things like that. Depending on your use case, Bayesian statistics, there aren't always easy ways to find that posterior. Sometimes you have to do a big integral and look over, the whole space of possibilities. But in the case of like Yoshi, what will she eat? There's just a couple of classes, however many foods we put in there, the mathematics are a lot easier. The posterior pops out of this. So after we've served her the squash, now you were correct, right? So what does that tell you about what we know about Yoshi?
Well, for me, it just confirmed that it was new and that she values something new, is curious, but then it's mushy, but not overly mushy. So I think she finds that interesting.
Now, it won't be new in the future. So what if Yoshi always tries new things, and now we're wondering, well, does she actually like the squash? Do you know right now, or do you need more data?
I need more data. We need to sprinkle in other squashes at different times with other options and to see what happens.
Yeah, if we want to have our beliefs get more converging to certain points where we have more certainty in some way, we definitely need more data. With more data, over time, Bayesian beliefs will converge to the true distribution. This is one property of them. And actually, Bayesian beliefs converge very quickly. We know that there's not going to come around somebody who invents a new competitive theory and says that theirs is better. It won't be, because you won't arrive at your posterior in exactly the fastest possible way on average. And the reasons for that get a little technical, but that's a good takeaway to remember. So being Bayesian is provably very good in many ways, and one of them is for some of its convergence properties. If we serve her squash again, in what way will your beliefs change in the future, maybe? Let's say she keeps eating it all the time.
Well, then I would assume that she just really likes squash. It must be one of her favorite foods.
Now, does she ever give any other behavioral indications besides eating something to show that she likes it?
Oh, yeah, she'll throw it out of her food dish.
If she doesn't like it. Yeah, so we didn't see that. What would your posterior beliefs look like if she had thrown the squash to the ground?
Then I would have been like, I guess she doesn't like it.
So one observation did tell you a lot, right? You went into it thinking 90%. Maybe you would have flipped to 10%. I don't know the exact magnitudes there, but something like that, right?
Yeah, well, another instance is if Yoshi really likes a food, she memorizes how it came to her. For example, what does she like? Chips. She knows the crinkly sound of the chip bag, so she memorizes it and starts to hear it. And as soon as she
Yeah.
hears it, she starts begging.
How does she beg?
Well, birds beg because they lean their head down and they start beating their wings.
Well, not exactly beating her wings, but like kind of shaking them nervously,
Yeah,
sort
it
of,
kind
right?
of looks anxious and anxiety producing. But
Yeah,
really, it's just her being very excited.
excitement. What about when she's served the food she so badly wants?
Sometimes she'll make a cute sound. Very rare. Maybe 10% of the time she'll go, eh.
Right, yeah. So that sound is information as well that we can integrate into our Bayesian model. We have observed that over time when she goes, that's like, oh, I really like this food. Or I really like, yeah, pretty much for food alone, I think. Does she use it in any other cases?
I've seen it mostly for food, actually. I guess she gets the most excited over food.
Right. So that's a signal now. When we hear that, our posterior beliefs should go up, right? We want to, after the fact, be like, oh, I guess she loves squash. So she didn't do that. So we know she's not necessarily, it's not her favorite food, but she likes it a lot. Had she made that noise, how much more likely would she be to eat the squash in the future than the reaction we actually observed?
I think she would have been a little bit more likely, but the thing is, I think sometimes she just makes the noise just because she gets excited at seeing her bowl. She doesn't eat it. She hasn't eaten it yet, so she doesn't know if she likes it.
Oh, okay. So this means we're not talking about the reliability of this signal. So when she makes that noise, most of the time, maybe 90% of the time, she's like, oh, I like this. But 10% she makes it because, I don't know, she was hungry or just happy for whatever reason randomly. So it's not a perfect measuring tool.
Her making the sound? Yeah, I mean, she's just excited for her food bowl and the way it looks.
Right. So we don't necessarily know which is which. Is she excited for a particular food or just the meal? That shows up in the likelihood part of the Bayesian formula. Now, what's also nice about being Bayesian is if you build everything correctly, it accounts for the fact that this is an unreliable measurement. It's still useful, but it doesn't tell the full story. So it's not like our beliefs just immediately go to 100% she loves squash. Our beliefs increase because it's consistent with the available information we have, but not all the way because it's not a perfectly reliable measurement.
Yeah, because I mean, we don't know exactly why she makes the sound. She's obviously happy when she makes the sound, but we're not sure why.
So to draw an interesting analogy, this comes up in robotics as well. So robots, whether they're factory robots or little toys or even autonomous vehicles, they have all this sensor data coming in, but sensors are flawed, just like human eyeballs and especially human hearing is quite flawed. Have you ever had an experience where you thought you heard something from one direction, it was the other, or something like that?
Yeah, one time my friend shouted across the lake, "Why don't we get Mediterranean deli?" And I heard, "Why don't we get peanut butter and jelly?"
Well, what did you end up with?
Well, once I said, "You want peanut butter and jelly?" And then they started laughing.
Why? Because they thought you asked if you wanted to go to the mall with Kelly?
I think they were just super surprised. And they were like, "No, that's not what we said."
Yeah, so sensors are not perfectly reliable. So you have to have some model of how good the sensor is. In our case, with the little cute squeal, that is pretty reliable, but not perfectly reliable. So we express that in the likelihood part of the function. So we take our prior beliefs, what we thought about whether or not she'd like the food. We update, in this case, given the absence of the squeal, she didn't make it. So we don't think, squash is her new favorite food, even though it could be. Maybe she just suppressed the sound today. And we wind up with a posterior belief. And then we can update that in the future in the exact same fashion with new observations. So I don't know if there's any squash left, but if she gets some again tomorrow and she does make the squeal and also eats a lot of it, well, then we would update our beliefs again. So our posterior from today becomes our prior tomorrow. And we update it with the new information we'll get, whether or not there's a squeal, whether or not she eats the squash, whether or not she eats something else in the bowl. And that will give us our new posterior beliefs that are the most up-to-date representation of our understanding of her preferences.
I just want to circle back. So when you said your current belief, it's like a distribution, but how do you get that down to a number?
Yeah, good question. So if it's a binary case, yes or no, well, it's an easy number. But in general, it's going to be a statistical distribution. So let's talk about the Gaussian distribution, or some of you may know it as the normal distribution. You have a mean and a variance, or I'm sorry, a lot of you will know it as the bell curve as well. So the mean is the middle of the bell curve. The standard deviation is kind of like how wide it is, and that can express your beliefs. So you can say that's like the GPS example. We assume that you're standing at the average of all of the available observations, and the standard deviation should get updated. If they're consistent, it should shrink because we seem to be in the same place. If they're wildly inconsistent, then it would get broader because we have less confidence in our belief over where you are. So belief is always a statistical distribution. Pick any point from all possible points, and I can tell you a probability it might be true.
So you're taking the probability and multiplying that.
Exactly, yeah. And in simple cases, like these like multinomial cases, yes or no kind of stuff, the math is pretty easy. It's just a lot of arithmetic, this probability times that probability. But when you have more complicated distributions, like maybe you're looking at something like earthquakes are accounted for, they're unpredictable and they're very rare, the statistics become much more complicated because there's not always a clear way to do the math, basically. In certain cases, and this is why Gaussian's a good example, using Gaussian distributions to describe your beliefs actually is a special case of a Bayesian thing called a Kalman filter. And people like it because all you have to do is find the new mean and the new variance. That's your posterior. You express it with two values, and there's a clear and computationally efficient way to take the old two values, update them given the new information, and arrive at the posterior. Basically, it's easy for computers to do. But if you have something more complicated, like, I don't know, the probability that one of the players who's playing Monopoly is going to win the game, well, there's so many twists and turns that'll shift the probability in this not very friendly way that there's no like closed form statistical way to do that. You just have to like run simulations and stuff. And that is where things become very computationally expensive. Either when the system is so dynamic, you have to run simulations, or when we know its statistical form, but there's no easy way to get the second stage, you have to do some complicated integral. In that case, maybe you approximate or something like that.
Well, I mean, I don't know. You said a lot. So if you're just going to simplify it for someone who's never taken stats, what's the short answer?
The short answer is think about binary variables. Does Yoshi like this? Yes or no? Not like the degree to which she likes it or something. Because the yes and no's, that's an easy way to express a prior because it's one value, the probability that it's true. And the likelihood can be updated in a very simple arithmetic way because we're going to also assume binary observations, like she did the cute squeal or not. So now, we have a probability over her preference, and then we know the mechanics, that she's maybe 85% likely to squeal if she loves the food. And then we can directly calculate for each of those four cases, what our prior belief was, and this model we have of what the squeal tells us, and we get a single value probability coming out of it. So that's sort of like the pen and paper way to be Bayesian. If you take away just one thing, it's that, we start with our prior beliefs. We have some model of the likelihood function, how likely we are to see different outcomes or things we can observe given our current beliefs. And we use that to compute the posterior probability, what we think is true after we've assimilated the new information.
So was all this Bayesian?
Yes, this is the very abstract ideas behind what it is to be Bayesian. I've just kind of said it in a nice conversational way, what it is in spirit. To be Bayesian, you have to follow Bayes' law, which I'll put in the show notes. As long as you follow the proper mathematical form, you are Bayesian. But the two key steps that you have to figure out is how do you express your prior and how do you calculate the likelihood function. Those are what you need to do the update. So anyways, yeah, we'll get into more Bayesian topics in the future. I definitely want to talk about Kalman filters and a few other updates. But I think that's pretty good for today. Thanks as always for joining me, Linda.
All right, sounds good. Thank you.
Thanks for listening to Data Skeptic, where the news may be fake, but the data doesn't lie. Support the show and find extended materials at dataskeptic.com.